Hello everybody, we are going to discuss the first chapter, measurement. So all the science begins with the measurement. So first of all, in order to start the science, we need to collect the data. So what are we going to cover in this chapter? So we'll deal with basic idea of science. What do we do in science? I'll show you the steps involved in the science. Obviously, most important thing is measurement. I'll show you what are the units. I'll discuss what is fundamental units and what is derived units. So we need to be comfortable with converging the units and most importantly the significant figures. So what is importance of measurement in science? In science, actually, we collect a systematic description of the knowledge about the universe, and in order to describe the universe you need to understand. So the description basically involves the measurement. So understanding demands the interpretation of the measurements or the data. So everything or the every physical process is the interpretation of the data or the measurements. Therefore, understanding the measurements is very important. Different methods are generated to collect the data. We are not going to discuss about that thing here, but we are pretty sure we encounter lots of examples of measurements in our daily life. For example, we see the temperature, we see the weather conditions, and we see the time. So all of these are the examples of measurements. And in science, can we measure everything within certainty? No, which is called error in science. And error, like in common sense, is not a mistake. Error or the uncertainty in the measurements is due to the limitation of the instrument. For example, if you are trying to measure the length of a table, for example, you are given a meter stick. Then if you remember the meter stick, this can measure the smallest length of 1 millimeter. So you can say the measurement of table at least within the range of millimeter. So you cannot go below that. So there is some kind of uncertainty always involved in the measurement. So in physical science, we cannot say the length of the table, exact length of the table, but we say that this is the lower limit of the length, this is the higher limit of the length, or we say that the length of the table lies within this interval. And most important thing is, like, whenever the object becomes smaller, the instruments, they do not become capable to measure such smaller measurements. So there is always some uncertainty in the measurement. So what is physical science? Physical science includes physical science, natural science include physical science and the biological science, but physical science include physics, chemistry, geology, meteorology, and astronomy. In this class, we'll discuss the fundamentals of each of them. we'll start with physics, and then we move to chemistry, and we move to geology and astronomy. Look at the picture of the science. The whole science is divided into social science and natural science, and you see here natural science, biological science. We do not care about this here. We talk about physical science, which include physics, chemistry, astronomy, geology, meteorology, and other science. So how do we carry the scientific investigation? So the first step is the measurement, right? So before taking the measurement, we need to observe the processes happening in the universe, and next thing what we need to do, we need to answer some of the questions, and those questions may be related with how the process happens and why the process happened, right? So we make lots of assumption, and scientists assume that the universe is in ordered manner, means we cannot include everything at a time, so we simplify the problem. In scientific method, we start with the observation, and we take the measurements, we simplify the problem, and we interpret the data, right? We reason the processes from which we make the prediction. So this can be broken down into these steps. The first step is observation, and then we take the measurements, we make hypothesis, and then we do experiment, and these experiments, with the series of the experiment, the observation or the hypothesis, if this becomes true, and if this is tested many times, then this becomes theory, and finally if this theory is verified over many times, then this becomes law. So we'll discuss this topic separately. So the first step is observation and measurement. So we gather lots of information here in the first step. The second step is making a hypothesis. This is a possible explanation of the observation, right? So this is a kind of educated guess. For example, matter consists of small particles that simply used as the building blocks of the matter, right? So you make some educated guess, and most of the time if you do the experiment, it should support your hypothesis. If not, then you need to repeat the process, and you need to change the ideas so that you can match with the hypothesis. So in this process, we design new experiments and test the validity of the hypothesis. So this is supported if it correctly predicts the experimental result, right? If not, then we need to change the experiment, or we need to change the parameters, and then we need to iterate the same process. The next process is experiment. So we do lots of testing under similar environment or within the controlled environment. Main goal is to support the hypothesis, and experimental results has to be duplicated. That means if you do some experiment here and if you get some kind of result over and over, then if the other people wanted to repeat the same thing, then they should get the same result. That is the way of doing science. So everything should be clear. Until your prediction is valid, it does not become an experimental result, right? So your prediction or the hypothesis should match with your experimental result. And then if this conclusion or the results from your experiment matches with your hypothesis, this will be tested for many times and this becomes a theory. So this is a tested explanation, right? For example, atomic theory. So this has been tested for more than 200 years. But the theory can be accepted, modified and rejected, right? It may change with the time, right? For example, people were using theory for bulk materials. When they discovered there are some other particles or the objects known as nanoparticles, so they figured that the theory for the bulk particles may not valid for the nanoscale materials. So again, the theory may be accepted or rejected. So once you are done with series of experiment and those theories are tested for many times, then it becomes a law, and which basically describes the process of the nature. For example, conservation of mass is one of the example of law. So the law is the concise form. It states some principle, but it is not self-explanatory. So in order to describe the scientific law, you need to make some models, you need to break into different parts, you need to make the models, means you need to draw the picture or the diagram, and then you can understand the law. So this gives you now the idea of scientific law. You see, the first step involved is observation and measurement. The second step is making the hypothesis. So what is the possible explanation of the observation, and then you do series of experiment. Basically your goal is to try to verify the hypothesis. Once you repeat the experiment for many times and if you get the consistent result, then it becomes theory, which is a tested explanation, and after series of verification, this theory becomes law, which describes the fundamental law of the universe. Now, in order to take the measurement, we need to know the system of units. So we are using standard units. So every physical quantity are the measurements. Physical quantity means that can be measured, has magnitude and its units. Most of the time these three quantities, length, mass and time, they are called fundamental quantities, and rest of the quantities are based upon these fundamental quantities. So study of the mechanics means in mechanics you apply force on the object and you looked at the motion of the object. So in order to, our next chapter starts with the motion. So in order to describe the motion, we need basically mass of the object, length or the distance, and the time. These are the three building blocks, and then we'll define other parameters from there. And what is a standard unit? Standard units means they are fixed, can be reproducible value to take the accurate measurement. And here is different system of measurements. Let's talk about the British system, because British system is mostly used in United States, where this fundamental quantity you see, length, is measured in miles or inches, right? And next fundamental quantity is mass. Mass is measured in pound, and time is measured in second. In metric system, the other system is called metric system or MKS system. In MKS system, length is measured in meter, mass is measured in kilogram, and time is measured in second. So US officially adopted this metric system, but still we are using British system. So what is length? So measurement of space in any direction, right? Space means either it could be length, width and height. So we are talking about the MKS system. Length is measured in meter. So 1 meter is defined as 1 by 10 millionth of a distance from equator of the pole, you see. So if you take the distance from North Pole to the equator, and if you divide it into 10 million points, then 1 meter, the one of the point defines the distance between one of the point, or the distance between 2 points is 1 meter. There is another way of defining the meter, is the distance traveled by the light in vacuum. So 1 meter is defined as distance traveled by light in vacuum, which is the reciprocal of velocity of light. 1 divided by velocity of light is pretty much standard 1 meter. Next quantity is mass. So what is mass? Mass is amount of matter present in an object. So we assume the mass is a constant quantity. SI unit of mass is kilogram. So 1 kilogram is defined as amount of water in a cube of 0.1 meter. So cube is a box which has same length, breadth and height. And see, this cube has 0.1 meter length, breadth and height. So if you put water within this cube and if you measure the mass of this water, this is exactly 1 kilogram. And currently 1 kilogram is defined as the mass of the cylinder made up of platinum iridium, which is kept at International Bureau of Weights and Measures in France. US prototype is shown here. So this is the platinum iridium cylinder of radius 39 millimeter, sorry, the height 39 millimeter, and the diameter of the cylinder is 39 millimeter. So if you take the mass of a cylinder of platinum iridium having this diameter 39 millimeter and height 39 millimeter, this will give you exactly 1 kilogram. And time is time continuous flows forward, has only one direction of flow, right? You know that. And the SI unit is second. So in British system or in metric system we use second as the standard unit. Originally this is defined as 1 by 8600 of a solar day. Now this is defined as oscillations of cesium atom in 1 second. You see the cesium atom makes this much oscillation. So in modern day this is defined as 1 second is defined as this much oscillations made by the cesium atom. Now you saw that there were three quantities we described before, which is essential for description of the motion. Actually those three quantities, length, mass and time, these are called fundamental units. They are called fundamental units or the fundamental quantities, right? Mass, length and time, these are fundamental quantities, and the units used for those quantities are called fundamental units. These are called fundamental units because they are independent to the other. For example, this length is the fundamental quantity, and this unit meter is the fundamental unit, and this is independent with other unit. For example, kilogram, mass is measured in kilogram, time in second, right? So there are other four. There are altogether 7 fundamental units. Electric current is measured in ampere, temperature is measured in Kelvin, amount of substance is measured in mole, and the intensity of light is measured in candela. So these are, you see, the physical quantities within the parentheses are fundamental physical quantities, and you see the units which are in black letters. These are fundamental units. And it is difficult to use all the measurement based upon the fundamental units. So you need to use derived units, means combination of the fundamental units. For example, volume is length times breadth times height, right? For example, if we take a rectangular object, parallel piped object, so volume is defined as length, breadth or height. Essentially you need three lengths along x, y and z direction. So what is unit? Unit is meter time meter time meter, so meter cube, or sometime you can see in CGS unit, this is centimeter cube. For example, area, length into breadth or length times length, meter square is the unit, so this is called the derived unit, right? Meter square is the derived unit, meter cube is the derived unit. For instance, speed is defined as length over time. Length is measured in meter, time in second, so meter per second is derived unit. You see here this meter is fundamental unit, second is fundamental unit, so meter per second is derived unit. Another quantity, for example, is density. Density is defined as mass per unit volume. Mass is measured in kilogram, volume in meter cube, so you see kg per meter cube is the derived unit, right? All right, now you need to convert some of the units, so you need to relate one unit to the other unit. For example, you need to convert British unit to metric system. For example, 1 inches to centimeter, you need to convert 1 kilogram to gram. So you need to know the conversion factor, and conversion factor is always provided in the book, or you can look in Google. So for instance, 1 inch is equivalent to 2.54 meter. Let's do some problem so that it would be clear for you. So how many centimeters are there in 65 inches? You see here 1 inch is equivalent to 2.54 centimeter. Now conversion factor means you make unit or 1 in one of the side left, either this can be either left hand side or the right hand side. So you see in first part, let's say in this case the first one is in red, you can write this expression in this way, right? When you multiply both sides with 2.54 centimeter, you get this result. Or you can write this in this way, right? Because this is the same thing. In this case, you are making this one, this side as 1, which is equivalent to 2.54 divided by 1 inch. So these are called conversion factor. And now what you are going to do, you have starting value 65 inches. You can either use this conversion factor or this conversion factor, but you need to be careful um, to choose the unit conversion factor, because so if you want to choose this conversion factor, the second one, you need to multiply. So when you multiply 65 inches with this conversion factor, you can cancel this inches here, because this inch is in denominator and this inch is in numerator, so this cancels out, and you need to multiply 65 with 2.54. Your answer is 165 centimeter. Still, you can use this factor also, but in this case you need to divide the 65 inches by this one, and if you divide 65 inches with this conversion factor, then this inches cancels out and this 2.54 jump to the upper numerator, which is equivalent to 65 times 2.54 centimeter, is basically the same thing. So you can use either multiplication or division to get the answer, but let's keep consistent with this. So use the multiplication factor and choose the conversion factor in such a way that you can cancel this unit with the unit in the denominator, so that you can get the desired unit here. So what is the rule? Let's discuss the rule and then we'll do some exercise. In step number 1, you can choose a conversion factor, or first of all you need to look at the relation. So relation can be found in a book or Google. In second step, you need to find a conversion factor. If you remember the previous slide, these are the conversion factors. So you need to multiply or divide. So we stick with the multiplication. So you multiply the starting value with the conversion factor, so you can get the answer. So you need to use the common sense to find the answer, right? Now, can you convert 50 kilometer per hour to miles per hour? And here is the conversion factor. 1 kilometer per hour is equal to 0.621 miles per hour. So how are you going to do that? This is your starting value. You need to make a conversion factor. So you need to cancel this kilometer per hour. That means your conversion factor looks like this, right? So what I did, I make 1 is equals to 0.621 mile per hour divided by 1 kilometer per hour. This is basically the conversion factor, right? Now this kilometer per hour cancels out with kilometer hour. Only factor left is 50 times 0.621, and the answer is 31.05. Is it clear? Okay, let's do other example. So can you convert 50 mile per hour to kilometer per hour? Again, this is the conversion factor. So you want to convert mile per hour to kilometer per hour. So you want to cancel mile per hour. So your conversion factor should look like this, right? Because you want to cancel mile per hour. So this should go down. You want to bring this thing down. So this is here and this is the final result. 50 mile per hour times this conversion factor. Mile per hour cancels out. You need to divide 50 by 0.621, and here is your answer. Okay, maybe a little bit difficult. If you are not comfortable with the mathematics, otherwise this is pretty simple. Okay, let's keep forward. So we started with the measurements. We studied how we do the science, how we take the measurement, and then we discuss about the fundamental units, what is derived unit. Now we know how to convert unit from one system to the other system. Now we need to figure out accuracy, error, and significant figure. As I told you before, error is synonym for the mistakes, but in science we call error as uncertainty, and every measurement has uncertainties. So if we are getting error, means we are not making blunders, but these are unavoidable facts. And everything, for example, physical constant, speed of light, distance from earth to sun, they contain some level of error or uncertainty because of the limited instrument. For example, measuring the speed of light has uncertainty of 1000 km. So we cannot have like instrument that can give you very precise measurement. So if you remember uh, what I told you before, if you want to measure the length of this table, so you can measure from the meter stick, you can measure at least millimeter. So the true length of the table may be 8.155 meter, right? Is that the true value of the length of the table? No. If you could find some instrument that can measure such digits after the decimal, so this could be more precise than this one, but there is no such tool. So at least you can measure, this is your length, measured length, and you have this limitation, and this is your uncertainty, means you can measure at least 1 millimeter, which is equivalent to 0.01 meter. So in physics, now you can say the length of the table lies within this limit. That means 8.155 plus or minus 0.001 meter. So if you subtract this, then you will get 8.154 meter, and if you add this, you will get 8.156 meter. And we say that the value of table lies within 8.154 to 8.156 meter. So we are not confident about the true value, but we can say that within this limit, this value should lie within this limit, right? So this 0.001 is the least count of the instrument, which acts as the error or the uncertainty. So this is the error or the uncertainty I was talking before. So we are good here. Now we can go to the significant figure. So what do we mean by significant figure? Is number of reliable digits in a given number. So looking at the digit, we can say that which digits are significant. For example, 3.21 centimeter has 4 significant figure. All the digits, they are counted here. For example, 0.062 has 2 significant figure because we do not count the initial zeros, right? So this is the law. Leading zeros are always insignificant. What about 80 kilometer? So this is the whole number, so it is ambiguous. So we are not sure whether this one has 1 or 2 sig fig. Could be, for most of the time we take this one. Means we can say that we don't know the exact precision, so we say that this one has 1 sig fig. We can pretty much say that the digit in the tens place is significant, but we are not sure about this 0. Or if you can write 80.0 like this, then this has 3 sig fig. Trailing zeros are always significant. This is rule number 2. Trailing zeros means the zeros associated to the right side of the decimal, and this is 0 before the decimal point. So leading zeros are always insignificant and trailing zeros are always significant. So can you tell me how many significant figures are there? 5. In this one, 7, because all the trailing zeros are significant. In 1500 miles, because this is whole number and we do not know about these zeros, right? Because we do not have decimal place, so 2. We are sure about the thousands place and hundreds place, but we don't know units and tens place, so 2 sig fig. This is the explanation for why 2 sig fig. So for example, if this could have been written in 1500.00 miles, then what is the sig fig? 6, right? Next, so if you want to divide 6.8 by 1.67, you will get this kind of result in your calculator. So are all these numbers significant? No. So we'll keep all the digits in the intermediate results and we'll round only in the final state. So how we are going to round the number, I'll discuss in next slide. So let's do rounding first. So if the first digit to be dropped is less than 5, then the preceding digit should unchanged. Means suppose you have 26.142 and you see here all the digits are significant here, right? This one has 5 sig fig, but you want to write your answer in 3 sig fig. Then what do you want? Like you want 26 point and another digit. So here you have 1 and then after 4. So this is less than 5. So you keep this number 1, 26.1. So if this number is greater than 5, then you need to increase by 1. So 10.063. So you have 5 sig fig, so you need to write in 3 sig fig. So 10 point, and you see here this is 6, right? 0 6. So this is greater than 5, so you need to increase the preceding digit by 1, means you need to increase this one 0 by 1. Is it clear? Okay, so this is the way we round off the numbers. So can you round 0.0997 to 2 sig fig? Remember the trailing zeros, sorry, leading zeros, they are insignificant, right? And you see here this 99, you want 2 sig fig, so you need to increase by 1 to this 0. So this is the answer. What about this? So for this one we need to go through some rules. So let's go to the significant figures for adding or subtracting. So for adding or subtracting, the answer is no more accurate than the least accurate number used. So least accurate number means least precise number. In this case, we look at the number of digits after the decimal point, right? If there is less number of digits after the decimal point, then this is called least accurate. So for example, in this case, if you add these three numbers, you will get this 14.1826, right? Now look at in this expression, 4.1 means there is only one digit after the decimal point. In this case, this one has only one, this one, the 10.07 has 2, and this one has 4. So this is the least precise number. So your answer should have one digit after the decimal point. That's why we rounded this 14.18 to 2. Is that clear? So while adding or subtracting, we go with the least precise number. Least precise number means those numbers which has least number of digits after the decimal place. So multiplication and division, this is different. In this case, we go with the least significant figure. For example, you want to multiply 11.2 and 6.7. 11.2 means this has 3 sig fig, 6.7 has 2 sig fig. So we should have, the answer should be 2 sig fig, the least significant digit, right? Least significant um, least significant number. Okay, so if you multiply this, you'll get 79. Sorry, you'll get 78.66, but you should have only 2 sig fig. Your answer should have 2 sig fig, so you rounded this up to 79. So this has 2 sig fig. So the general rule of significant figure. So let's do some of the example. If you want to add these two numbers, you will get this 16.797, but while adding you need to go with less precise number, which means you need to have 2 digits after decimal point, right? This is the least significant number, least precise number, so we round this up to 2 places after the decimal, so 16.80 is the answer. Why? You know this, right? Because we take the least precise number. So when you divide this, there are 2 sig fig, 3 sig fig here. So while dividing, we go with the least significant number. So this one has 2. So your answer should have 2 significant figure. So you rounded this thing to this. Okay. And this is the answer. 6.8 has 2 sig fig. So summarizing the sig fig, all non-zero digits are significant. For example, 23.4, 234, they are all significant, so they have 3 sig fig. Zeros are significant if they lies in between two non-zero digits. See here, this has 4 sig fig, this has 3, because they are in between the non-zero numbers. So leading zeros are not significant, right? So we don't count these zeros, so this has only 2 sig fig. Trailing zeros are always significant, so this one has 3 sig fig, but 4500 for the whole number, right? Without decimal place we are not sure, so most of the time we take these two as the sig fig, so 2 sig fig. So rounding off the numbers, we already discussed this, right? So we stop there. So what is the answer for this one? This is the multiplication, so we go with the least significant figure because this one has 3 sig fig, this one has 2 sig fig, so your answer should be 2 sig fig, but you look at here, this has 3 sig fig, so how do you round this? 1800, right? You round like this. So now your answer is, you have this 1 and 8 significant, so this one has 2 sig fig. Clear? What about this? This is division. So this one has 3 sig fig, this one has 5, and this one has just 2. So your answer should have 2 sig fig. 2 sig fig means your answer is 7900, right? Let's do some exercise. So how many significant figures are here? 1, right? Because we are not sure about these units and tens place. What about here? All the digits are significant. whatever here. Leading zeros are not significant, so 2. And this is called scientific notation. So in this case you don't have to worry about this 10 to the power, so this one has 2 sig fig. In this case we are multiplying, this one has 2 sig fig and this one has 3 sig fig, so we go with 2 sig fig list. We are adding and we go with test precision, so 2. Okay, alright, we are done with this chapter. The most important thing is unit and the significant figure. The rest of the part is how do we do the signs. So I believe you get enough idea about the units and the significant figure. I'll post the homework in sapling, so please go through these slides, and if you have any questions and concerns, please use your discussion board for your questions. Okay, have a good week. So I'll keep posting the other lectures too soon. Have fun. Thank you.